Titrations are used to measure exactly concentrations of acids and bases. As we know, when you put an acid and a base together, you're going to get neutral water. The H3O plus ion is going to connect with the OH minus ion, and you're going to land up with H2O. The other ions in the solution don't play a role in the neutralization. We call them spectator ions. They're just watching the reaction happen. Neutralization, however, does not always result in a pH of 7. Most of you will know that the pH scale goes from 0 to 14, with 7 being the midpoint and neutral being 7, generally considered. However, if you're doing an acid-base titration, we call it neutralization, but it's actually equivalence. It's often known as the equivalence point, and that is when the acid and the base have reacted so that neither one of them is in excess. In other words, you have the same amount of acid and base. Strong acids and weak bases will reach their equivalence point somewhere below 7. Why? Because the acid is going to win the fight. Equal numbers of moles of acid and base together, the acid is going to ionize very well. The base is going to dissociate quite badly, so you'll have a lot more H3O plus around in the solution. You can use an indicator called methyl red. There's another indicator called methyl orange, and they are good to use for titrations because they actually change color at a pH somewhere slightly below 7. Then you've got, if I were to take a weak acid and a strong base, so in other words, the acid ionizes badly, the base dissociates well, you'll have more OH minus in your solution at the point of equivalence when there's an equal number of moles of both of them. And that'll happen at some or other pH above 7. And the indicator that you can use for that is called phenolphthalein. When we're doing a titration, we can do the following. We're actually going to put acids and bases into a burette and a pipette, and I'll show you the exact method of doing a titration in a minute. So your pH is going to be somewhere above 7. Truth be told, most of the time we're going to be looking at either a strong acid and a strong base, or a weak acid and a weak base, and then you're going to get neutralization happening at the neutral midpoint of 7. And the best indicators for that are litmus or bromothymol blue. So when you're setting up a titration, this is more or less what you're going to land up with. You're going to first take either the acid or the base, and you're going to measure out a fixed amount, an exact amount. A pipette has got a little graduation mark where you can see exactly how much solution you're getting. And this thing is called a pipette. You'll put it into something called a conical flask. The conical flask will then be put next to the retort stand, and then you use something called a burette, and a burette has got graduations all the way down over here. So you take what's called the initial reading, and you put a little bit of indicator into your, let's say, acid solution, and it's not impossible to do this the other way around. In other words, you could have the base there and the acid there. It doesn't really matter. But in this case, your acid's down here. And you then start pouring this base into the acid using the burette tap until such time as the indicator changes color. And then you take a reading again. Let us say, for argument's sake, that the reading over here, if you were to put your eye neatly over so that you don't have an error of parallax, let's say you had 45 centimeters cubed, or milliliters if you prefer. And down here, when you did the same thing, you land up with, let's say, 15 centimeters cubed. Then the volume of base that would have been put into that solution is going to be, and you just do a subtraction, 30 centimeters cubed. So the official definition, titration, a base is slowly added to an acid, or vice versa, until an indicator changes color. And you use the right indicator to get the right equivalence points. Titrations are usually performed to determine the concentration of either the acid or the base. One of the solutions has got a known concentration, and what do we call a solution with a known concentration? A standard solution. And the other solution is unknown. You will remember that number of moles can be expressed as concentration times volume, or concentration is number of moles divided by volume if you prefer. And this is true of both the acid and the base. The volumes can be in any unit as long as they are the same when I'm doing a calculation with this particular methodology. But if you're going to go to moles per cubic decimeter, obviously you need to put the volume into decimeters cubed. But it turns out that once you've done the whole circle, it cancels out. The values of the number of moles of acid and the number of moles of base are obtained from a mole ratio from the balanced equation. So how am I going to use this now to be able to solve a problem? A solution of sodium hydroxide contains 2,5 grams of sodium hydroxide in 250 centimeters cubed of solution. That is my standard solution. So let's calculate that I have got number of moles is equal to mass over molar mass. And so it's 2,5 divided by the molar mass of sodium hydroxide is 23 plus 16 plus 1, which is going to be 40. Which means I land up with 0,0625 moles of the sodium hydroxide. Concentration is equal to number of moles divided by volume. So that is 0,0625 divided by 250 centimeters cubed is going to become 0,25 decimeters cubed. Remember, you divide by 1,000 because of the cubic function. So that's going to be 0,25. So that's going to be equal to 0,25 moles per cubic decimeter, which I can abbreviate to a capital M, in other words, molar solution. So that's our standard solution. I'm now told that I've got 24 centimeters cubed of the solution is neutralized by 20 centimeters cubed of a sulfuric acid solution. What is the concentration of the sulfuric acid? I'm going to need to write a balanced equation. Sodium hydroxide plus sulfuric acid is going to become sodium sulfate, and sodium has a valency of 1 and sulfate has a valency of 2, so it's NaSO4, a salt plus water. I now need to balance that, so I'm going to put a 2 in over there, and I am going to need to put a 2 in over there, and then I think it is a balanced equation. Now that I've got a balanced equation on that, I am able to establish my volumes that I've been given of each. So I have got 24 centimeters cubed of that and 20 centimeters cubed of that. I'm going to go the long way, but there is a shortcut and I'll show that to you afterwards. So the first thing I'm going to do is I'm going to say, how many moles have I got over here? Number of moles is equal to concentration times volume, and that is going to be equal to 0,25 times by 0,24. I prefer not to change, to leave the units the same, because it's not authentic in the middle. Even though it comes out in the wash, it's not really true in the middle. So I prefer to change that into decimeters cubed by dividing through by, sorry, it's 0,024, dividing through by 1,000. Here we go. And getting an answer. And I land up with 0,006 moles. I then look at a mole ratio between sodium hydroxide and sulfuric acid is 2 is to 1, and I'm going to 0,006 becomes 0,003. I then take that number of moles up here and I can work out my concentration. Concentration is equal to number of moles divided by volume, which is 0,003 divided by 0,02, because again I've got to convert that into decimeters cubed. And I land up with a concentration which is equal to 0,15 moles per cubic decimeter, which again is molar. I'm going to show you the shortcut method now, which I'm not overly fond of, but here it is. You can say number of moles of acid over number of moles of base is equal to volume of acid, concentration of acid over volume of base, concentration of base. And now we can substitute all of the values in. Number of moles of acid I get from the balanced equation 1 over number, this is a B over here, over number of moles of base, which I get as 2. That is equal to the volume of the acid. The volume of the acid was 20. The volume of the base was 24. The concentration of the acid is what I do not know. And the concentration of the base I worked out. Where did we find it? Here it was 0.25, which we had worked out earlier by determining the concentration of the standard solution. When I rearrange that in my calculator, I automatically get the concentration of the acid to be 0.15 moles per cubic decimeter. -3. So this is a quick little way, it's a shortcut. It's called a monkey see, monkey do kind of formula. Whilst what I've shown you over here is an actual understanding of the number of moles and a molar relationship between these two things, the acid and the base, in order to create the salt and the water.